Bismillahirrahmanirrahim. Assalamu alaikum viewers. In today's lecture, we are going to discuss regression estimates with more than two independent variables that we call multiple regression with more than two independent variables. And then we'll learn how to use the data analysis tool pack of Microsoft Excel in order to estimate regressions with more than two independent variables, although Microsoft Excel's data analysis tool pack has some limitations. For example, it estimates regression equations with maximum number of 16 independent variables. After moving through the data analysis tool pack, we'll discuss concepts like adjusted R-square and p-values and some other concepts that you will be seeing in the Microsoft Excel data analysis tool pack's output in multiple regression. So in today's lecture, first we move to regression estimates with k independent variables. In the slide, you are seeing a complete multiple regression equation where you have several variables from x1, x2, x3 through xk. So we have k plus 1 parameters in this case. So this multiple regression is estimated in the same way as we estimated the simple and multiple regression equation with two variables. Remember that we minimize the sum of squared residuals. We find some normal equations. We solve the normal equations simultaneously and get the values of the parameters. So there is nothing new or different in estimating a regression equation with more than two independent variables, although it is a bit complex and some things also change, as you will see in little time. So to estimate a multiple regression with k independent variables, we usually have k plus 1 normal equations. These normal equations can be calculated or can be estimated through simultaneously solving the normal equations. You also can use various formulas in Microsoft Excel. You will be using the Microsoft Analysis Data Analysis Tool Pack because yet you have not learnt it. So first we will move through line st command and then data analysis tool pack. So in today's lecture, you will be seeing also some outputs of regression, and we'll explain the concepts of adjusted R-square, regression coefficients, p-values, t-statistic, whatever you will be seeing in the regression output. So as I told you, there is nothing new in estimating a multiple regression with more than two independent variables. It is a bit complex. You have a greater number of equations and you may consume some more time. So we have software for helping us. So the software has made life easy. So you had seen the line st command previously, in which we can estimate the regression equations with up to about 50 independent variables. In data analysis tool pack that we'll be discussing today, we will be able to estimate multiple regression equation up to 16 independent variables, but we'll have a nice output regression matrix which will give the almost all the regression results that you require in t-test and f-test, etc., as you have already learned. So in the slide, you are seeing a list of some points that are different in Microsoft Excel's multiple regression. And not only that, in general, multiple regression with more than two independent variables is a bit different from simple regression, although I told you there is nothing new. First of all, as you increase the number of variables, you will observe that the degree of freedom is becoming less and less. That means that you need or you may need a larger number of observations, because with a smaller number of observations and a smaller degree of freedom, the results may not be reliable. You may face some more problems when you have more than two or three independent variables. For example, multicollinearity can be an issue. Multicollinearity is the correlation between the independent variables of the regression equation. We'll be learning about multicollinearity in later lectures. We also can observe that as we move to two or more independent variables regressions, the formula for standard errors would be changing. As you saw that the formula for standard error of b in the simple regression equation and the formula for standard errors in the regression equation with two independent variables was slightly different. When you move to three variables, there is a difference in the formula again. So the formulas change a little bit. That means that you need more t-statistic. For example, if you have three independent variables, you will have to perform three tests of significance, for example, t-tests. And you will have to perform the same usual goodness of fit test. So most of the things are the same. The estimation procedure is the same. You minimize the sum of squared residuals, but normally you have a complex method. Normally we use matrices in order to estimate larger equations or equations with more than 2 independent variables. But presently you have learned how to replicate the manual procedure in Excel. Today we'll be learning a very useful analysis tool pack and how to use it to perform multiple regressions. Another thing in multiple regression is that software has their limitations. As I told you, Microsoft Excel has a limitation of 16 independent variables, and Stata or SPSS or SAS, other softwares, can estimate regression equations of variables up to, say, 64 variables or more in some versions of that. So every software has the limitation, but in most of the cases, you wouldn't be needing equations with more than, say, 15, 16 variables. So Microsoft Analysis Tool Pack would be useful in this case. There is a very useful data analysis tool pack available with Microsoft Excel, although you may have to install it. It estimates regression equations for up to 16 independent variables and produces a nice output of regression statistics, which you can interpret and use in your research papers. So basically, Microsoft Analysis Tool Pack, Data Analysis Tool Pack, uses the line st or straight line command in Microsoft Excel and uses line st to perform regressions and reports the regressions in a standard tabular form, which is almost similar to the tabular form you may observe later in Stata or SAS or other software. More or less, the regression output is the same in various software. In Microsoft Excel, we'll be learning how to use the data analysis tool pack. But before that, I'll tell you how to install the Microsoft, or it is an add-in, so you have to add it to Microsoft Excel. Sometimes it is already installed, and sometimes you have to install it. So in today's lecture, we'll be learning how to install it and how to use it and how to interpret the results. So you will be seeing various slides which indicate how to use Microsoft Excel's data analysis tool pack after installing it. You may have various versions of Microsoft Excel, for example, 2003, Microsoft Excel 2007 or 2010. We'll be basing our display or presentation of how to use Microsoft Analysis Tool Pack on Microsoft Excel 2010. Although I'll be telling you what to do in Microsoft Excel 2003 as well. So you are seeing in the slide that we have presented how to start installing the data analysis tool pack in Microsoft Excel 2003, 2007 and 2010. In Microsoft Excel 2003, you will click on Tools, on the menu Tools, and then Add-ins, and you will be presented with different add-ins. You will add the data analysis tool pack. It will be installed automatically. The second one is Excel 2007's Office button. You are seeing the Office button. You will just click on, it is on the top left in Microsoft Excel 2007. You will click on the Office button and then look down. The second last item is Excel Options. You will click on it. You will have the Add-ins Manage, Excel Add-ins in the selection box. You will click Go. You will select the add-ins Microsoft Excel's data analysis tool pack. You will observe that you have two data analysis tool packs. One is with Visual Basic and another without it. Use the one without VBA. In Excel 2010, you will click on File, which is green in color, and then Options, and then Manage Excel Add-ins in the selection box, and then you will click Go. In the same way as you can do in 2007, you will select the Microsoft Excel add-in, the data analysis tool pack, without the VBA, and you will click Go. You are seeing that you click on the File menu, which is green in color, and then the second last option shown by the arrow is Options. You will click on Options. When you click on Options, you will be presented with a list of various add-ins available in Excel. If you find the data analysis tool pack over here, this means that it is already installed. You just need to tell Excel to add it. If you don't find it, you may need a CD of Microsoft Office to install the data analysis tool pack. So in this window, you will click on Add-ins indicated by an arrow, and in step 4, you will be selecting Microsoft Analysis Tool Pack without VBA, and after that, you will click Go. Maybe Microsoft Excel asks you that the data analysis tool pack is not installed. Do you want to install it? You will click Yes. After checking the box in front of the data analysis tool pack, you will click OK, and the installation process will start. in a minute or two, your data analysis tool pack will be installed. Now we can start by entering your data in Microsoft Excel. It is better to have a data set already so that you can move in Microsoft Excel with me to perform the data analysis tool pack and learn. Basically, there are 19 options available in the Microsoft Analysis tool pack. One of the options is regression. So the first step in Microsoft Excel is to enter your data. Remember that to use the analysis tool pack, your independent variables must be placed together. The columns should be adjacent to each other. So first you will have your dependent variable, and then you will have the columns containing your independent variables, which may be from 1 to 16 independent variables. The data analysis tool pack wouldn't be able to perform regressions for more than 16 variables. So you are seeing 4 columns here. Y is your independent variable. X1, X2, and X3 are your independent variables. We have 10 observations for each variable. So in Microsoft Excel, it is better to have title of the variable as I have shown, Y, X1, X2, and X3, and you have the values. You can copy and paste from different locations into one sheet, or if you see that the independent variables are placed separately, you can combine them. This is the first step. Without having the X's or the independent variables together, you will not be able to perform the data analysis. So in the first step, you will enter your data in a manner that you have the independent variables together in adjacent columns. To perform the data analysis, you must click on the ribbon called Data, and then you will click on Data Analysis. You will find it on the rightmost side of the data ribbon if you have installed the data add-in, Data Analysis Tool Pack. A small window will appear. You will scroll down, or with the arrow key, you will find regression, because as I told you, there are 19 different options available in the Data Analysis Tool Pack. One of them is regression. Presently, we are focusing only on regression. You will select regression and click OK. As you are seeing, another window appears near your data. In this window, you have to give 2 or 3 or more inputs. 2 are necessary. One is the input Y range, which is the range of your dependent variable. You will give the references of cells for the dependent variables. For example, the data lies in, say, C3 to C12 over here. And then you will click in the input X range and drag your mouse and select the X variables, as many as they are. For example, you have 3 variables in X. You will select 3 of them. This is an array, basically, not a column. You will be observing different items in this window. For example, you have an output option. You can display your results on the same sheet by giving the output range. You can display your results in a new worksheet, which is already checked, as you are seeing. And then you can ask some additional statistics, for example, residual plots, etc. So these are basically additional statistics that you ask Excel to provide with the Microsoft Excel regression output in the Data Analysis Tool Pack. So the steps are as follows. First, you will enter your data. The columns should be together better. First, the dependent variable and the independent variable columns. Remember that you can have maximum 16 independent variables. So you will click in the input Y range. By dragging your mouse, you will select the Y observations from the first cell to the last one. And then you will click on the input X range. And by dragging your mouse, you will select all the X variables. And presently, I'll request you to select the option Display the data in new worksheet as it is indicated by the arrow. And don't ask additional statistics. We can do that later. First, learn how to run the Data Analysis Tool Pack and explain the regression results. So after you have done this, you will click OK. Now you are seeing the regression output in Microsoft Excel, which has 3 parts basically. We'll be explaining each of them in due course now, today. The first one provides regression statistics. The second one is ANOVA, as you are seeing, in which you have the F statistic and sum of squares, etc. And then you have basic regression output, which provides the coefficients, the T statistic, the P values. We'll be telling you what are these things. What are the P values, what are the standard errors, etc. Some of them are already computed by you. You have the degrees of freedom, etc. in the ANOVA. You have the basic regression coefficients and standard errors and t-statistic in the regression output. Now we discuss them one by one. You are seeing the results of the regression output in a new sheet in Microsoft Excel. When you clicked the data analysis tool pack and gave your options and said OK, the regression was performed and the results were displayed in a new worksheet. As I told you, there are three basic parts of this regression table or regression metrics. The first one are regression statistics, the second analysis of variance, and the third are basic regressions, that coefficients, standard errors, etc. We'll be discussing everything one by one, but before that, I would advise you to resize your columns by selecting the columns and increasing the width of the columns so that you can look into the observations clearly or the results clearly, because you see we have fractional values based on, say, more than 4 or 5 or 6 decimal places. The first part are regression statistics. We have various items here. The first one, as you are seeing, is multiple R, which is 0.99899. This is basically the multiple correlation coefficient or the square root of the coefficient of determination. Multiple correlation coefficient is computed with the help of various partial correlation coefficients. The second item is called coefficient of determination or the explanatory power of the model, or R square. In this second item, the value is 0.9979, which is the square of the previous value. This shows the explanatory power of the model. In this case, we'll say that 99.79% of variation in the dependent variable is explained by variation in the independent variables. We can capture 99.79% variation. So R square is a good indicator of the explanatory power of the model. But as you see, this is a very large R square, as R square lies from 0 to 1. So 0.99 seems to be very good. But you will come to know that regression may have some kind of problems, like multicollinearity. So we suspect some problems and we test for them. This is the later process in regression. The third item is adjusted R square, which is 0.9969. It is computed with the help of the coefficient of determination, but it is adjusted to the degrees of freedom, because you will observe that as we increase the number of independent variables, the R square increases. So maybe R square is overstated. So to overcome this problem, we adjust the R square by the formula you are seeing, R square minus 1 minus R square into K minus 1 over N minus K. As the number of independent variables increases, R square will be overstated. So this is why we have made this adjustment. The next item is standard error. This is the standard error of estimate defined as summation E square over N minus K square root. You have already computed that. The last one is number of observations. In this case, we have 10 observations. So these are the basic regression statistics, which is the first part of the output that you got from the data analysis tool pack regressions. In the second part, you have the ANOVA. The first column shows regression, residual, and total. The second is degree of freedom. You are seeing the values 3, 6, and 9. Basically, 3 is your value, K minus 1, where you remember K is the number of restrictions imposed, which is equal to the number of parameters. So if we have 3 independent variables, we'll have 4 parameters because we have an intercept as well. So we have 4 parameters in this case, so K minus 1 is 3. The residual degree of freedom is N minus K, that is 10 minus 4, which is 6. And the last one is N minus 1, which is 9. Now you are seeing the sums of square and mean sums of square. Basically, we have the regression sum of square, the residual sum of square, and the total sum of square. If you divide this sum of square by the degree of freedom which you saw in the previous column, you will get the mean sum of square. Now look at residual sum of square, which is 16.945. Basically, this residual sum of square is the value of summation E square, square of residuals, the summation of the square of residuals. And the value 8422.5 or 8422.5, which is the total sum of square, you can indicate as summation y minus y bar whole square. As you computed in the goodness of fit test, we have the F statistic over here, which is 992.05. F is used in the goodness of fit test, and we want to know whether the fit is good or no. Previously, we used the F statistic and compared it with the table value at 5% degree of freedom or 1% degree of freedom. But this time, you are seeing that we have the significance of F indicated as, you are seeing 1.7803 E minus 0.8, exponent minus 0.8, or 10 raised to power minus 0.8. This means that actually this value can be read as 0.0070178. So this is a very small value. Now let me explain this significance of F. It is the level of significance at which our calculated F becomes larger than the table value. So this is a very small value. If this value is less than 0.1, in this case it is, we'll say that the test is a good fit at 1% level of significance. If the value is greater than 1% or 0.01 but less than 0.05, we'll say that the model is a good fit at 5% level of significance. And if this value is above 5% or 0.05 but less than 10% or 0.1, we'll say the fit is good at 10% level of significance, because this 1%, 5% and 10% are the traditions that we follow in research. If the value is above 10% or greater than 0.1, we'll say that the fit is not good. So this significance value computed by the data analysis tool pack shows the level of significance at which your F statistic will become equal or larger than the table value of F, and your model will be a good fit. In the third part, you have the regression statistics. First, we have the coefficients. The first one is intercept, 280.39. This is your value beta naught if you use the usual notations of regression equation. So this is your intercept, or the value of the dependent variable when the value of the independent variables is 0. The second item is minus 0.04. This is the coefficient beta 1, the coefficient of the first x variable, indicated as x variable 1. So this is your beta 1 if you use the usual notations. Similarly, next one is beta 2, and the final one is beta 3. So you see that they are negative values which indicate that the variable y is dependent on the variable x1, x2 and x3 in an inverse manner. So it changes in opposite way when you change the variables x. So these are the coefficients. You remember that we perform some kind of individual variable significance test before interpreting these coefficients. For example, you are seeing here standard errors. These are the standard errors of the coefficients which you calculated in the individual variable significance test. Look at the second value, which is 0.03. This is the standard error of beta 1. Remember that the formula for standard errors of the beta coefficient changes when you increase the number of independent variables. For example, when you had one variable, you had another formula. When you had two variables, the formula slightly changed. So when you had 3 or more variables, it will again change. So it is better that the software provides you with these values. So remember that we divide the beta coefficients by the values of their standard error, and we get the t statistic, which is used in the individual variable significance. So if you divide the previous column, the coefficients, by this column, the standard error, you will get the value of t statistic, which you are seeing now. For example, the t statistic for the first x variable or first coefficient is minus 1.2, and that for the variable 2 is minus 13, and that for variable 3 is minus 0.49. All of them are negative. Remember that if your betas, your slope coefficients are negative, your t statistic also will be negative. Now there is a special thing that you must understand. It is called p-value. A little while back you saw that you had the significance value of f, which showed the level of significance at which the calculated f becomes equal or greater than the table value of f. In the same way, this is that level of significance at which our calculated t statistic becomes equal to the table value, or it becomes greater than the table value, and the beta coefficients become significant. So remember that traditionally we use 1%, 5% or 10% level of significance. So if these values are less than 1% or 0.01, we'll reject H0 in the individual variable significance test and conclude that the beta is significant. or the variable has a significant effect on the dependent variable. In the second case, the value is 0.24, which is the p-value for the first x variable. Multiplying by 100, you have 24.4%. This means that if you have a level of significance of 24.4%, then you can say that the beta coefficient is significant. But remember, the maximum level of significance acceptable in research is 10%, which is very high. Usually, researchers prefer 5% or 1% level of significance. As you know, this is the chance of the probability of type 1 error. So as this is above 10%, we will accept H0 and conclude that the beta coefficient is not significant, or the variable x1 seems to have no impact on the variable y in the population. So look at the next value. It is written in the notation with a value e minus 0.5, which means you have to multiply it with 10 raised to power minus 5. This means you have to shift the decimal point to the left side by 5 digits. 1 is the first digit, you will shift the decimal, and then you will need 4 zeros. So this value will be read as 0.00001003, which is very small, which is less than 0.01 or 1%, which means that this beta coefficient is significant. You will reject H0 in the individual variable significance test and conclude that beta 2 is significant. The variable x2 seems to have a significant effect on the variable y. The next is 0.63 or 63%. Again, this is not significant in the same way as you did above. So basically, p-value is equal to the probability that the absolute value of t statistic is larger than the tabulated value of t statistic. The tabulated value is the value that you get from the t distribution standard tables. So you can say that this is the level of significance at which the calculated t statistic becomes larger than the table value, and you can reject H0 at this level of significance. So obviously, if it is less than 1%, it is very good because your coefficients are significant. If it is less than 5% but greater than 1%, you will conclude that the coefficients are significant at 5% level of significance, and so on. You just saw the regression output of Microsoft Excel's data analysis tool pack. It was very nicely presented because Excel provides you with regression statistics, ANOVA, basic t statistics, f statistic, r square, standard errors, whatever you need in presenting the results of a regression equation. So it was a nice output. And it is similar or identical to the output in different software that are used for regression. So, but this is not free from limitations. For example, the first limitation that you must have observed is that we cannot perform regressions of more than 16 independent variables by the Microsoft Excel data analysis tool pack. Basically, this data analysis tool pack uses the line st command or function in Microsoft Excel. The line st command can perform regressions of up to 50 variables. So it is very good. But the limitation of this Microsoft Analysis data analysis tool pack, the Microsoft data analysis tool pack, is that you can perform only regressions with up to 16 independent variables. Another problem is that you must have the x's or your independent variables together placed in the columns adjacent to each other. There shouldn't be gaps. The columns of the independent variables should not be spread. The Excel spreadsheet sometimes miscalculates regression statistics in case you have severe multicollinearity, because it doesn't take care of different problems like multicollinearity, heteroscedasticity. There are no functions available for that. So these are the few limitations that you may face while using Microsoft Excel's data analysis tool pack. So what is the solution? We'll be using other software, sophisticated software like Stata, SAS, SPSS, eViews. We'll use one of them and we'll perform better regressions which will take care of problems like multicollinearity, and will be performing tests of heteroscedasticity and other tests which detect the problems in the regression. Because this is not the final answer. You have got a good regression output, but you may need to test for possible problems. For example, possible violation of assumptions of ordinary least square. As you have studied the Gauss-Markov theorem, you have some assumptions. For example, the errors should be normally distributed, etc. So if you don't take care of these assumptions, the results that you saw in the Microsoft Excel data analysis output would be misleading. So the story doesn't end here. In further lectures, we will be discussing how to detect and test for these problems. Now you are able to perform the regressions with the help of Microsoft Excel data analysis tool pack. Let's take a practical example. The first step is to find some data. For example, you can download data from various websites. You can use different surveys. For example, in Pakistan's case, you can use the Economic Survey. You can download data from finance.gov.pk or the State Bank of Pakistan website. International data can be downloaded from various sources. For example, you can look into the World Development Indicators. You will be able to find data on the World Bank websites in the World Development Report. If you go through the IMF website, you would find that they have an annual publication called International Financial Statistics. You also have various panel data sources. You have websites that provide free access to the data. Normally, US data is free to access. In some cases, you will have to pay for accessing data. You have data available in soft copy, as well as you can look into hard copies of the Economic Survey, World Development Reports, International Financial Statistics, etc. Today we'll have a practical example to how perform regression on actual data using the Microsoft Excel data analysis tool pack. So you will be going to the World Development Indicators, which is a site of World Bank. So I'll show you in the slides how to access and retrieve data from these websites. The World Development Indicators provide financial and economic data for more than 180 countries, for more than 60 years, for more than 100 various variables like GDP, interest rates, exchange rates, GDP at constant prices, GDP at current prices, etc. You are being presented with the website address, that is data.worldbank.org for organization. This is a World Bank website. It contains data on world development indicators. Note this address, place it in your browser, and click enter. You will be reaching the website that may provide you actual data, international data, macro data, financial data for more than 180 countries. When you open the site, when you view the site, when you visit the site, you will see on the right side that you are presented with a button, a bluish button, Data Bank. Click on the Data Bank. On the right side, under Resources, you will find this Data Bank. So when the page loads, select in countries Pakistan, because you have access to data on almost all countries, which includes Pakistan. Presently, we focus on Pakistani data. So you will be asked to select some countries, some variables, and some time periods. In the end, you will be asked to retrieve the data in an Excel format, Stata format, or other format, CSV format, for example. So first you click the data bank. You will be presented with a choice of countries. You will select Pakistan as a country. Then you will click on series. This makes you able to select the variables. You will see there are a lot of variables here, maybe more than 100 variables. So in this case, you will select GDP at constant 2005 US dollars. Labor force, gross fixed capital formation, again in constant 2005 US dollars. Exports, etc. So confine yourself to these variables so that you have a small regression table and you can easily interpret the results. So before moving forward, let me explain to you what is this constant 2005 US dollars. In fact, the values in current prices are presented which don't take care of inflation. So you have a price deflator. If you divide the values by the price deflator, if the price deflator has a base of say 2005 and your data is in US dollars, and you divide your data in current prices by the price deflator, you will get all the data in constant 2005 US dollars. So we have taken care of inflation because some rise in the values of the variables, for example GDP, may be due to inflation. So in this case, you will select 4 variables. You can use the filter. If you look into this selection, there is a filter given above. You can click on the filter and write or type your variable. For example, if you type GDP and enter, you will be presented with all the variables that include the term GDP. So it makes the selection of variables easy. Now click on time and select the years from 1991 to 2012. There is another option. You can select all the years, and when you get your output, you can delete the years that you don't require. After you have made these three selections, that is the selection of country, you may select more than one country, the selection of series, this is the data series, the variables, and the third one is time, the years for which the data will be downloaded. When you have done this, click download. You will be asked about the format in which you require the data. So you have data in CSV format, Excel format, etc. As presently you are using Microsoft Excel, so we'll prefer Microsoft Excel version, Microsoft Excel format for the data. There is another format there, CSV, which means comma separated variables. This is very useful. So in comma separated variable file, you can use this file in various software like Excel, Stata, SAS, etc. So presently, we'll download the version in the format in Excel. So when you download, the file will start downloading and you will get a Microsoft Excel file which presents the data names, the data codes, and the actual observations from the years you have selected for the countries that you have selected and on the variables that you had selected in this selection. So the process that you are seeing here on these slides includes three steps. One, to select country or countries. Second, to select a data series or the variables that you require. Because if you select all the variables, you will have very heavy files. You can download a zip file as well from here which contains more than 70 MB data on international financial and economic variables. But don't do that, it would be very heavy file. So after that you will select time periods. Also, you tend to select all the time periods, but this again will create heavy data files, so better select the years that you require and then download the file. You will have a file in Excel format. Now we'll be running the regression on this actual data. But before running the regression, you must reshape the data. You are seeing that the data is in a wide shape. So you have variable names and various years, and this is for Pakistan only. So to perform regression or use the data analysis tool pack, you will be reshaping the data. You can copy the data, click somewhere else, paste special as a transpose of the data, and then the data will be in a proper format. As you see in the next slide, we have the regression output that is performed with the help of data analysis tool pack on actual data. Now let's try to explain what do you see. As you know, we have three parts in the regression output. One is the regression statistics, second is ANOVA, and third is the regression statistics like coefficient, standard error, t-stats, p-values. So as this is on actual data, let's try to understand what is seen over here. So first, your R square is 0.997, which is very good. But as I told you previously, that there may be some problems. We will be testing for these problems. For example, multicollinearity, heteroscedasticity, autocorrelation. But presently, as you don't know about them, so you assume that the explanatory part of the model is truly given here as 99.7%. So in the regression degree of freedom, you have a number 3, which indicates k minus 1. As you had 3 variables, the value of k was 4, and k minus 1 gives you 3. The number of observations was larger, so you have a residual degree of freedom of 19. And the total degree of freedom, which is n minus 1 of 22. This means the number of years in your data was 23 years. Then you have the sum of squares, mean sum of square. Most important is the F statistic, which is 2000 something. So as you see, the significance value of F is 3.71 E minus 24. This means multiplied by 10 raised to power minus 24, which means you have to place 23 zeros after the decimal point and then 371. This is a very small value. So as this is very small, less than 0.01, so your test is a good fit. The fit which fits GDP as a function of labor force, gross capital formation, which is a proxy for capital stock, in this case, maybe not a good one, and exports, which may be an indication of openness. So the fit is good in this case according to these statistics. Now move to the coefficients. Variable 1, 2 and 3 give the regression coefficients. For example, the first one is 2081. This is the coefficient of labor force. This means 1 unit increase in the labor force will cause the GDP to increase by 2081 US dollars. These are in constant US dollar prices, remember. Same type of interpretation can be given for the other two regression coefficients. Now look at the p-values. You learnt that if the p-values are less than 1%, the beta coefficient is significant at 1%. If they are less than 5%, being larger than 1% but less than 5%, the beta coefficients are significant at 5% level of significance. In this case, you can see that variable x variable 1 and x variable 2 show a p-value of less than 0.01. This means that beta 1 and beta 2, which are the coefficients of labor force and gross capital formation, are significant. So you can interpret their results safely if they are free from further problems that we are going to study. The variable 3 shows a 54% level of significance or p-value, which means that as is above 10%, this is not significant. So you will state that the variable 3, maybe it was exports, I think, so it has no significant impact on GDP. So this is a simple demonstration of how we can use the data analysis tool pack on actual data. You downloaded some data, try more downloading from different sites, and try to perform regressions and try to interpret your results. Although this is a raw form of presentation of results, but slowly you will come to know how to perform regressions and how to interpret your results if you keep on trying. So as you will move forward, you will come to know that we have various problems in regressions and we have to address them as well. So the story doesn't end here. There are some possible problems in regression results. For example, number 1, the relationship may not be linear. As you saw, we performed a linear multiple regression. GDP on labor force and gross capital formation and exports. So we assumed that these 3 independent variables and the dependent variable are linearly related. So in real life, normally we don't find linear relationships. So this may be called a wrong specification. So when you wrongly specify the model, you may have misleading results. Similarly, you may have ignored some important variables because maybe human capital may be affecting GDP. So you can find some proxies of human capital like literacy rate, like expenditure on education as a percentage of GDP, or expenditure on education as a percentage of your annual budget, and so on. Maybe you are missing other values as well, other variables. So this is a missing variable problem. So number 1, you may wrongly specify your model. So instead of specifying non-linear, exponential or logarithmic models, you are specifying a linear straight line. So if you misspecify your model, you will have misleading results. Second, you may have forgotten about some important variables or ignored them, or due to lack of availability of data, you may not be able to include them. So there may be many reasons. So this is a missing variable problem. So you have wrong specification, you have missing variable. Okay. Some of the indicators may not be appropriate. For example, as I told you, we have taken exports as an indication of openness. The country is open to the world. Normally we take exports plus imports. We have other indicators as well. So maybe this is not a good indicator. This may be a good indicator, but we have to test for that. We'll be doing in the later stages. Also, there may be some abnormal years. For example, if you include in your data series abnormal years, like years in which you had war, or there were terrorist activities, or you had some crisis in your exchange rate, etc. So the values will be outliers. So outlier is a problem. It affects the regression results. So you should scan your data through different graphs like scatter diagrams and so on to see whether you have outliers or no, whether you have an abnormal year or no. Also, you remember that we had various assumptions in ordinary least square. For example, the errors should be normally distributed. You have the Gauss-Markov theorem. We should know whether these assumptions are violated or no. If the assumptions are violated, the results will be misleading. For example, the errors may not be normally distributed. In that case, you will have problems. The problems may include one or more of multicollinearity, heteroscedasticity, and autocorrelation. So first, you have a wrong specification. Second, you may be missing some variables. Third, you may be using inappropriate instruments or inappropriate indicators of some concepts that you visualize or thought of. You may have outliers or abnormal values. In abnormal years, the errors may not be normally distributed. And there may be problems like multicollinearity, heteroscedasticity, and autocorrelation. So as I told you, these regression statistics are very good. They seem to be nice, but you have to be careful to address all these issues that we discussed after discussing the regression output.